Okay, welcome to the lecture number 57. So, we have been discussing about the control moment gyros, the satellite actuated with control moment gyros. So, we will continue with that. Okay. So, it is a basically a gyroscope put on the satellite, but there are certain modifications. Okay. So, let us discuss about that, but before that I want to discuss about few subtleties which I told in the last lecture, which is quite important. Okay, so, in a basic gyrostat, what we have that there is a satellite body, main body, which we have written as B, and inside this there is a wheel which is rotating on its axis, but this axis remains fixed, which we are showing as A, or either we have considered that the same thing can be something like this. I have a satellite and outside this there is a wheel. So, this wheel is rotating about this axis. So, it is a rotating, this wheel is rotating. Okay. So, these two cases are same, only thing here this is outside and this is located inside. Okay. In both the cases, with respect to the satellite main body, if you see that if I fix any body frame here. Okay. So, this axis of rotation which is here in this direction, which is here in this direction, with respect to this frame it remains fixed, it is not changing. Okay. So, this is the characteristic of a basic gyrostat. Now, once we were discussing about the control moment gyros. So, the difference there was that I have a satellite here. Okay. Inside this there is a control moment gyros, which we have made it something like this. Say we have shown one outer frame and this frame is pivoted in this satellite. So, this axis is fixed in the satellite, this axis is fixed. Okay. So, the fixed axis. Then we have the inner frame or the inner gimbal, and thereafter we have a wheel which is rotating here. So, this is a wheel which will be rotating about this axis. Okay, shown by dotted line means it is on the back of this figure. Okay. So, here in this case what we see that the angular momentum of this wheel, let us show it by some other color, this wheel is rotating about this axis. Okay. So, its angular momentum I can show it by h. In this case, with respect to this body axis, this is the body axis. So, with respect to this axis, this direction is fixed, but here in this case what happens, this is one gimbal. So, satellite can rotate about this, sorry, this frame, the brown frame, this is the brown frame is rotating here, brown frame rotation here, and in this place this is the pink frame rotation takes place. Okay. So, this way you can see that this vector, the h vector which is looking here like this, because of this pink frame rotation, it will rotate to this direction, okay, and it will become like this. Okay. Say this is initially horizontal, so it will come to this position. So, the change position will look like it has gone from this position to this position. Okay. So, this change is taking place, this is the delta h, initially this is h. Now, after this, once we rotate about this axis, okay, once we are rotating about this, the brown frame rotation axis. Okay. So, in that case, this will then go down, what you have seen here. So, better I will make the figure little bit, I will change it. So, let us say this is the h vector initially, and from here then it is changing to this position. So, this is your delta h, removing this. H t plus delta t. Okay. Thereafter, what is happening that because of the rotation about the brown frame, so this rotation has taken place. So, this angle is say the psi or delta psi, whatever. So, brown frame rotation will take it down. Once we have given this rotation, and thereafter we are giving the brown frame rotation. So, that we can indicate by some other color, say this is going then down. Okay. So, this is one plane movement, and thereafter this is going down. So, this vector is from this place to this place, it comes here in this plane, and then it is going down. You can see that how it is looking. Okay. So, that means this h vector has changed from this place to this place finally. Okay. While here in this case, so this rotation is with respect to the body frame which I can fix here in this place. Let us say this is our E 1, E 2 and E 3 direction. Similarly, here this is E 1, E 2 and E 3 direction. Okay. So, in the gyro state, this direction remains fixed. So, this is fixed. Okay. While here in this case, this axis is fixed, but this axis is not fixed. You can see that this axis will also rotate. If you rotate it like this, so this axis will move from this place to, it will go to this side. From here to here, it will look something like this. It will move from this place to this place, okay, by psi angle. So, neither this axis is fixed, neither the this rotation vector or the h vector which I am associating with the angular momentum of the this wheel. Okay. This is neither remaining fixed, because this will change due to this also and due to this also, because of this and because of this also. So, this case becomes complicated as compared to the gyro state. So, this is the difference between the CMG and the gyro state motion wise, and there are other things also which are different. So, I will point out the related mathematics, and it is a very important what I told yesterday in the last class. So, now let us look into the what we have been discussing about the single frame control moment gyros or single gimbal control moment gyro. This is also called, we can write as single gimbal control moment gyro. So, for the single frame or the single gimbal control moment gyro, what we have looked at, this is rotating on certain axis, okay, and there is a wheel okay, and this wheel rotates about this axis, and here let us say this is rotating about this axis. So, it is a angular momentum vector, this is h, and we will assume for the time being that this is massless, okay, but is rigid. Okay. This is an idealization, massless but rigid. So, as a result what will happen, that as soon as you rotate about this axis, this frame will tilt, okay. It will come from this place to, it will rotate about this. So, it will look something like this. This part will go inside, okay. It will go inside from here to here, this will come outside, and this part will go inside. So, this is the part which is inside here, this is the part which is coming outside. So, that means, if I rub this part, and there is a break I am showing, that it is going from the back. So, you will find on the Google the single, the SGCM and the DGCM, means double gimbal control movement gyros, DGCMG, this we call as the double gimbal control movement gyro. So, as soon as we are rotating, so this will also tilt, okay. It is a rotation vector, it will tilt from this place to, it will come from here to here, and this will go from this place to this place, means the rotation axis will come to this place, and then your disc will be oriented like this, means the h vector now it is a tilted. Okay. So, this is now the h vector, and assuming that the wheel is rotating at a constant speed, this angle we can show this is the theta angle. So, here theta dot will be present here in this case. So, what happens here, that the change which has taken place, this is your this place to this place. Okay. So, better we can show here in this place. So, this is your delta h, and as I told you, the corresponding torque generated, as we have been discussing, that will be delta h divided by delta t. Okay. Here this is not because of the speeding of the wheel is rotating at a constant speed, okay. But the rotation axis is getting tilted, okay. You are tilting the rotation axis. So, if you tilt the rotation axis, so magnitude wise what we have seen, and also the vector wise I have shown you, this can be written as, if I write here in this direction, say if I take, I fix one axis to the this frame, the blue frame. So, this axis I take it outside to the blue frame, and this axis is going here. If I write here I cap, j cap, and in this direction k cap. Okay. So, delta h by delta t we can write as theta dot j cap cross magnitude wise. First, let me repeat what I have written last time. So, that I have okay. So, this delta h we have written as delta h magnitude, basically this is delta h divided by delta t magnitude wise. So, delta h is nothing but this h vector times this angle which is delta theta, okay, or here this is delta theta. Okay. So, we write here as delta theta, this one divided by delta t, this is times not cross, this is multiplication, simple multiplication. So, this is h times theta dot. Okay. And the same thing in the vector notation can be written as omega cross h, where omega here in this case is theta dot j cap, and h here in this case say it is in the k direction right now. So, we can write here h times k cap, and therefore, theta dot h j times k cross k, that becomes I cap. So, this is basically here in this direction. So, the torque generated lies along this direction. Okay. So, this is your tau, this is the torque output. So, we apply certain torque about this axis, you have to apply here torque. So, this is called the input axis, and this is the output axis. So, that means this torque, as you can see, this will be a result of this torque. I can show it like this, because this is coming here in this direction. So, this is going down, one force is going down and one force is coming up. So, here the force is going down and this is coming up. So, it is something like this, say one side force is going down and one side the force is coming up, and this is the I axis. Okay. So, the torque produced is along this axis. You can see that this is the using the right hand rule. So, tau is here in this direction. Okay. But you can see that from this figure little this is slanted, it's I cannot show you in the 2D like this. So, this is a better view here in this place. So, this one actually this line and this line, they will be parallel to each other. Okay. So, this means if you look from the if I tell you that basically this will be perpendicular to the page at the center of the rotation wheel, this tau vector, it will come perpendicular, it will come out from the page at the center of the wheel, and that will be perpendicular to the page. So, that means this the axis which is shown here, this axis, it will be perpendicular to this. Okay. So, but here these two axes are fixed to the satellite. Okay. So, these two axes are not free to rotate, and therefore, if this is inside a satellite, say this is the satellite body. Okay. So, this whole thing will make, there will be a torque about this axis, means this blue axis which is shown here, it is going like this and it is coming here in this direction. Okay. So, this whole satellite will then rotate about this axis, because there is a output torque about this axis. So, we have applied a torque about this axis, and as a consequence we are getting torque output along this direction. So, this is the principle of the control moment gyros. So, this is single gimbal control moment gyros. In the double gimbal control moment gyros, I hope this is clear, that because of this constraint, okay, this is a rigid constraint. So, it is not free to rotate, this cannot go down and this cannot go up. Okay. It cannot go down and this cannot go up, and therefore, it cannot rotate about this axis. So, where this torque will then go? This torque will then, therefore, it will be acting on this whole body and it will move the whole body about this axis. Okay. So, using the control moment gyros, we can reorient the satellite, and this single gimbal control moment gyro is it can produce very large torque. In the terrestrial, like for the ship, okay, there are big control moment gyros to say this is the ship and going in the water. Okay. So, there are very large control moment gyros which are used for controlling the ship, because it is a million of tons, its a weight is there. Okay. And such a big ship like the aircraft carrier which are there, aircraft carrier these are very heavy, something like the 5 million tons. Uh, 5 million or 5 lakh, let me call, it is a 5 million ton. So, this is quite heavy. So, to control this, if the waves come and this gets disturbed, so to control this you require very large amount of torque. Okay. So, that torque is generated using this control movement gyros on the ship, and those control movement gyros are very large in size and they can produce enormous torque. Single gimbal control movement gyros, it is somewhere 100,000 Newton, what we call as the 1 lakh Newton meter torque can be generated, okay, for the terrestrial case, okay, using the single control movement gyros. It is a very large. Okay, in the double gimbal control movement gyros, as we have discussed that we have the outer frame which is pivoted in the satellite. So, this is in the satellite body. This is an exaggerated figure, okay, it does not consume so much of space. Thereafter, we have the inner gimbal which I have shown like this. So, this is the gimbal axis here, you rotate by theta here and about this by psi. So, there is a motor which can fixed to this one, this the brown one is outside. So, brown one is outside and this is inside. And then we have the rotor, okay. So, this is pivoted here, so it will rotate about this axis, this will rotate here and this will rotate here. So, theta dot we can show here, psi dot we can show here and then phi dot we can show here in this place. So, this figure earlier also we have made, but how the actuation takes place today we are discussing about this. So, say I call this again as the input axis. If I do this, so if I apply a torque is applied using a motor about this axis. So, what will happen? This will go down, okay. This will go down. So, we have to show it, this will come from this place to this place like this and on the upper side it will go like this, and then we need to join this to get the respective frame position. Okay. So, this is the new frame position. Okay. Now, in this situation what is happening? that as the h vector, which is say here in this case, if I show this axis like this. So, this is your h vector for this the rotor, and as usual this is we are assuming massless, and this ring also we are the inner frame also we are assuming massless. Okay. So, this h vector which is here, this is the corresponding h vector for this rotor which is rotating like this. Okay. So, this will go down, this goes down by angle here delta theta. Okay. So, if we look from the horizontal position, so this will be almost like a vertical. Okay. So, this is your delta h. So, what we have discussed earlier along the same line, the torque produced will be theta dot times h, but this time the direction is vertically downward. Okay. Means the output axis is along this direction. So, this is output axis. So, as a result of this rotation, this vector, the vector which was here, the h vector, this tilts from this position to and it comes to this position. So, this is your delta h. So, delta h is basically here in this direction. So, this is your torque direction. So, this quantity we can write as theta times h, and if I write here say in the outer frame, if I define this as the k, and so with respect to the outer frame, this direction is k, and this we are showing as I and this as j. So, the outer frame if it rotates by psi, so this will rotate, it will rotate from this position to this position, this will go from this place to this place. So, this torque if you look, so this torque is using the right hand rule, this torque is going down like this, okay. And using the right hand rule, how we can produce this torque? This is tau. So, this is equivalent to force applied like this in the horizontal plane. Okay. So, this is the force applied in the horizontal plane, means it will cause this external gimbal, or this is the outer gimbal, this is the it will cause this outer gimbal to precess. Okay. So, and so how the satellite will be then controlled, how you can change its orientation, that is the question. So, the solution is you do not allow the rotation here in this place using a motor. Whenever it is required, you release it, and whenever it is not required, you use the motor, that this torque is nullified. Okay. So, a large amount of torque will be needed to cancel this. Okay. The torque about this axis. So, you will need a motor here in this place, either here in this place or either here in this place to cancel this torque. Okay. So, if you cancel this torque, means it is becoming something like a rigid frame, it is a fixed, instead of here a gimbal, it is a becoming fixed here. Okay. It is a becoming fixed, it is not a gimbal, no more rotating. Okay. So, this torque will be directly transferred to the satellite then. Okay. So, in the as compared to your single gimbal, you can see that you have to use a motor to restrain it, so that this frame does not rotate, and this torque generated here it gets transferred to the satellite main body. Okay. So, that the satellite can rotate about this axis. So, therefore, the satellite can rotate about this axis as shown by this figure. Okay. So, the extra motor that you use here in this place, one motor you are using here in this place, which I am showing, let us say this is one motor, okay, and one motor we are using here in this place. So, this extra motor here, it consumes extra energy consumption. and therefore, this double gimbal control moment gyro, this is not as economical as your single gimbal control moment gyros is. So, this is not as economical as the single gimbal control moment gyro is. Okay. Means this is consuming more energy, consumes more energy. Also torque wise, because if you try to produce a larger torque, so you need to produce put a bigger motor here in this place to restrain it. So, that is not good, and therefore, the torque production capacity of the double gimbal control moment gyro, it is lesser than it is less as compared to the single gimbal control moment gyros. So, this is the basic principle involved for the control moment gyros. Now, we can discuss the related mathematics. So, we will continue discussing about this topic about the control moment gyros. So, say this is the block diagram I am showing, this is the spacecraft. So, this is your spacecraft. Thereafter, I have one block here, so, in this case, for the spacecraft, this is the spacecraft, and then for this you have the attitude control system. Remember that your control moment gyros is internal to the system, and therefore, there is no external torque acting on the system as a whole. If you think that a gravity gradient itself acting for a short time, in the short run if you are just looking. So, you can ignore that, the aerodynamic torque, then the other like the solar radiation torque and so on. So, we can neglect those things. So, if we neglect, so the system it becomes free from the external torque, okay. And in that case, the system angular momentum will remain conserved. So, your attitude control system, which is inside the body, just like the control moment gyros and all this, while there is a difference between the this type momentum transfer, these are called the momentum transfer devices. While here, if you look for the thrusters, so I can have a thruster here in this place, I can have a thruster here in this place, this produces thrust and this produces thrust. So, using this I can create. So, say this is producing thrust here in this direction. So, this thrust goes here in this direction by arrow, and this thrust it is here in this direction. So, I can produce a motion about this axis, okay, which is going inside or coming outside, it does not matter, this rotation is taking place like this. So, these thrusts they act like external torque, okay. This forms a couple, okay. So, this force, let us say this is F and this is minus F. So, they cancel each other, but the torque remains, and this kind of arrangement is used on the spacecraft if you are using the thrusters, okay. Because this does not require any internal moving devices. Okay. You can have one chamber of propellant, and that propellant can be expelled to create the necessary force or generate the necessary force, and which will result in the corresponding torque. So, these are acting as the external force here, while here the control and therefore, acting as an external torque also. While the control moment gyros, the gyrostat what we have looked in, these are all angular momentum conserved system, means whatever is there it is inside. Okay. You can see that the satellite is speeding up, but just opposite to that, because the total angular momentum is conserved, h total, this will be h body and plus h will, this is going to remain constant. Okay. This is not going to change the total quantity, not the right hand side, left hand side is constant. If you speed up the wheel, so this will also speed up, but as a whole the angular momentum is going to be a constant if there is no external torque. Okay. So, the attitude control system, now this consists of we can put it outside. And I make a box here. So, this whole thing is a attitude control system, and out of this these are the subsystems. So, attitude control system, and then you have the momentum, angular momentum basically, angular momentum control system. Inside this we will have the momentum control devices, which is angular momentum control devices. One or many can be there. So, we can write here devices. And to support this device, then we can have the corresponding moment, this we can write as the MCS. MCS is your momentum control system. So, MCS, this is subsystem, means what other things are required to drive this. Okay. So, what are the other things we can expect? The basic electronics, then the corresponding software or the algorithm, software slash algorithm, this can be like the control algorithm. Then vibration control subsystem, vibration control even for this, and of course, other things, associated things can be here in this place. But for this system, attitude control system to run, okay, you need to know the attitude of the satellite also. So, for this then you need the sensors. So, this sensor can consist of like the attitude sensor, okay, what is the attitude, and also the angular momentum sensor, angular velocity sensors, angular rates sensor, means along the different axes you are measuring the angular rates. and here the other actuators can be there, such as say the magnetic torquer, it can be thruster also. So, thruster can also be there. So, whatever you can expect, so in the other actuators we can put it. Okay. And there are other things, other subsystems which are other subsystems. One very important thing for the satellite is the cooling system, which we call as a thermal system. It is a thermal protection and cooling. One side of the satellite which is away from the sun. So, this is facing very low temperature, extremely low temperature, and the side which is facing the sun, it will face a very high temperature. And if the satellite is, say, it is rotating slowly, okay, in 1 minute it is rotating on its axis only one time. So, for 1 minute it will be facing the sun almost one side, or say for the half minute. So, so if we look this way, so satellite undergoes the cooling of the structure and heating of the structure. So, this generates these are called the thermal stresses. Okay. So, you need proper management for that, otherwise many system can fail. In the case of the Chandrayaan, the same thing happened. In the case of the Chandrayaan, exactly it is a why it failed once it was put in the orbit. So, there was the temperature control problem, and because of that some of the sensors failed, and those sensors once it failed. So, satellite attitude cannot be known, it is a and therefore, it became very difficult to manage. So, what they did, they increased the orbital radius, means here this is the moon. So, initially the satellite is in this orbit. So, they raised the orbit from this place to this place, and thereafter whatever the data could have been transferred. So, they got it, but the purpose of the satellite was lost. So, they could not control the satellite because of the failure of the sensor. Okay. So, these things are very important. So, the subsystems, then the structural subsystem, many things, associated things can be there. Okay. Then the communication, you need to communicate with the ground. Then your power system, you need onboard power. So, on the satellite, if this is your satellite, you will put solar panels on both the sides, or other designs can be there. Okay. Then this actuator system, here inside that the propellants and other things you are storing. Okay. So, we can write here as the thruster. Or the propulsion system, thruster / propulsion system. And if man is going in the satellite, that vehicle, so then the life support system should also be there. So, it is a very complicated. If you look on National Geography or any of the Discovery channel, so you find that how complicated the structure inside the satellite is. Okay. So, this is a basic idea about fabricating a satellite. What are the things you can expect? So, you can find many books available on the satellite system design, satellite system design. So, that gives you a fairly good idea about what are the design requirements, okay. What are the problems you are going to face while you are designing the spacecraft. So, everything will be there. Okay. It will not discuss there the attitude control system in details, but this will give you brief idea about what the attitude control system is. Okay, so we stop here and then we will continue in the next lecture. Thank you very much.